preparing continental, then food is tested. Okay, then like that we have this data. Now thing is that if I ask you, if cook is Sita, mood is bad, cuisine is continental, is the food tasty? So this is the question we want to answer. So answer must be yes or no. So it's a binary, but that is a two class problem. So this is nothing but the outcome. This is outcome, and these three are my input features. So this is my x. So I can call this as x1, this as x2, and this as x3. And these are uh, omega 1 or omega 2. So like that we have to form the problem, and the data here, if I consider the problem number 1, then cook is equal to Sita, mood is bad, and preparation is continental. Okay, so these are inputs. Question is my food tasty or not? Now, if you look at the table carefully, for Sita, I have only these two samples, and one with good mood and one with bad mood. And if I search for the combination, Sita and mood is bad. So Sita mood is bad, and preparation is Indian. So I don't have data which is Sita mood bad and continental. So if I search for the probability, if I search for the probability, then there is no evidence of this particular thing, that cook is Sita, mood is bad, and cosine is continental. So probability will be 0 in that case. But that should not be the case. I have to answer it using whatever data is given to me. So best way to solve such kind of things is use naive Bayes. So what we assume that x1, x2, and x3, these three variables, that is cook, mood, and cosine, they are independent of each other. So there is no relation within these variables. If I find relation that Sita and bad and continental, then there is no evidence. So if I search for cook equal to say Sita and mood is bad, so there will be and here, and there will be one more and here, that cosine is continental. So such combination do not exist in my table, then I cannot answer such kind of questions. But the way out is that we assume all the variables are independent. So cook, mood, and cosine, they are now independent. Now what makes the things, now if I assume that, then I can answer the following probabilities. If cook is equal to Sita, given condition is taste is yes. So for this kind of data, I can search in my table. Now when I search for cook is equal to Sita, I don't care about mood and cosine. So this x2 and x3, I don't care. I just care about x1. So I just go to the table and I check that this is data for Sita and both are yes. How many yes do exist? So this is 1, 2, 3, 4, 5, 6. So out of 10, probability of yes is 6 by 10. Obviously, probability of not tasty food is 4 by 10. So this is my prior knowledge. This will be my prior knowledge. Now out of this yes, how many times Sita is present? So there are 6 incidences of yes. Out of that, there are 2 incidences where Sita is present. So 2 by 6 is the probability of this particular thing, that is cook is Sita and food is tasty. Now I take the second variable. So this is due to the first variable. Now I go for second variable. Mood is bad given the condition food is tasty. So now when I consider x2, I don't care about x1 and x3. So I just go to the 6 samples which are tasty, and then I check whether there is any mood equal to bad. So these are 6. Then you see that this is bad when the food is tasty, and one more yes. Okay, this is bad, then this is good. Okay, so there are 2 samples which are with mood equal to bad within the domain of tasty food. So again it will be 2 by 6. So this is 2 by 6. Then we go to the third variable, that is x3. Now what I want that cuisine is continental and food is tasty. So now I don't care the variables x2 and x1. I just care about x3. Just go to the 6 samples where uh, taste is yes. So there are 6 samples, and out of that, how many times continental appears? So this is 1, and this is another continental. So 2 by 6 again. So 2 by 6. So you just see how we calculated these probabilities. Okay, so when I calculate the probability for cook equal to Sita, I don't care about x2 x3. When I calculate mood equal to bad, then I don't care x1 x3. When I go with cosine equal to continental, then I don't care about x1 x2. So like that we have calculated 3 required probabilities. Obviously we have already calculated this probability of testing. Now what I want, this is my x. This was given to us in the problem. So this was my x in the problem. What x is? X is cook equal to Sita. Mood is bad and cosine is continental. So this was given to me. Now I call these 3 as capital X. What is the question? Question is, with this X, capital X, is my food tasty? Okay, so is my food tasty? So that is the question. So we can solve this using Bayes. Here we will solve using Naïve Bayes. Suppose I write here probability of tasty is equal to yes, given input is X. Now capital X means all those 3 variables, so that we can use regular Bayes. Then I will write here X given tasty is equal to yes into probability of yes divided by probability of X. So like this we can calculate. Now this particular term, now we are replacing using naive Bayes. So this particular term I am replacing. Suppose I write here, this will be probability of Cook equal to theta given yes into probability of mood equal to bad into probability mood equal to bad given as into probability of Hussein is continental given yes. So this product I should write here. Okay, so that will be my likelihood. So this is the approximation using naive Bayes. So if I do that, then I come to this equation where I just write these three probabilities. These three probabilities are here in this bracket multiplied by the probability of yes, that is 0.6, and then I just divide it by, so this division by p of x I am writing here as some alpha, some constant. Okay. So if I calculate this, then it will be 0.0216 by alpha. Now we have to calculate the other side, because I have to answer whether the food is tasty or not with given input, that is capital X. So we have to now solve for test is equal to no. Okay, so we follow the same steps. Only thing is that now here I have to say test is equal to no. Earlier it was test is equal to yes. So let us see now. So probability of Cook equal to theta, and given the thing is test is no. So first of all, let us mark the samples where there is no test. Okay, so these are I think 4 samples where test is no. Now let us check for Cook equal to theta. So this is Asha, then this is Usha, Asha, and Usha. So as such, there is no data for theta. So there is no data for theta, so I should write there 0. But if I do like this, then the whole calculation will be 0, and there is no fun in doing this thing. So be careful in such problems. We replace, if I write in red here, we replace such 0 probabilities by a small number. Now here suppose I am replacing it by 0.01. So this is a crucial thing in this problem. So whenever you find there is no evidence, so you can replace there is no evidence by a small evidence. Don't put big values like 0.1 or 0.2. You put a small value, maybe 0.001, but you don't write there simple 0. If you put simple 0, then all the other probabilities will get multiplied by 0, so there is no fun in calculation. Now next step is go to the mood equal to bad when there is no tasty food. So we have 4 samples, as I said. Now I am concentrating on just mood. So mood is bad. So mood is bad here. Mood is bad here. Mood is bad here. So in general, whenever mood is bad, I can say that there is no test. So 3 out of 4 cases are like that. So 0.75 is the probability. Then I go to the next variable with test equal to no, that is cosine is continental. So in third variable, when there is no test, you check. It says continental, continental, continental. So whenever we prepare continental, food is not there. So 3/4 is the ratio. So it will be 0.75. Now this probability, that is posterior, when test is not present with this given input x, if I want to compute, then I should replace this by no and this also by no, and this p of x in the denominator is as it is. So this calculation are again based on when there is no test. So I just consider those samples where there is no test. So we have already calculated this particular product. So I just see here 0.01. This is the replacement to the 0 probability. Then I put this 0.75 here, this 0.75 here, and the posterior of not tasty food, because there are 4 samples out of 10, so it will be 4/10. Then divided by probability of x, so I'm writing it as alpha here. So if you multiply, so this will be a small number like this, and the earlier one is here. Now as probability of tasty is equal to yes, given the input x is greater than probability of test equal to no given x, I can declare that x is classified belonging to tasty class. Okay, so you can see that I have not calculated value of alpha or value of probability of x. Without calculating that, I can directly tell you what is the answer. Now, if at all I want to do that calculation of perfect probability, I know that the probability of test equal to no given x plus probability of test equal to yes given x is equal to 1. Okay, so probability of test equal to yes given x plus probability of test equal to no given x, this is equal to 1. So I substitute the calculated probabilities in terms of alpha here, and I equate it to 1. Okay, so this 1 by alpha will be common out, and the alpha is this value. So if I substitute alpha in the probability of test equal to yes given x, so which was I think 0.0216 divided by now 0.2325, then probability of test equal to no given x. So this was 0.00225 divided by 0.2325. So that will be 0.93 and 0.07. Okay, so these are exact probabilities by after calculation of alpha value. Now from here you can clearly see that this is the highest, the largest probability. So what is meaning is that with this given input x, that is cook is Sita, mood is bad, and cosine is continental, whatever we prepare is tasty. So test T is equal to yes. That is the answer. Now similarly, you can solve after this class. If cook is equal to Asha, mode is equal to bad, cosine is continental, is the food tasty? So now I'm just replacing cook from Sita to Asha, and you have to answer same thing. I hope you can solve this. If you find any difficulty, we can discuss tomorrow. We can take one more example. Now, this is some data of vehicles. So there are 10 samples, and features are color of the vehicle. So I can call this as X1, type of the vehicle, and origin of the vehicle, and outcome, whether it is stolen or not. So assume that there are 10 samples with us like this. Color is say red, sport, type of the vehicle is sports, then origin is domestic, it is getting stolen. That is the outcome. So like that we have a table. Now question is, if color is red, type is SUV, origin is domestic, will it be stolen? So whether this thing is there in our data set, we can check. So color is red, so this is red. And then you have type SUV, so this is SUV. Origin is now imported, so we don't have any data with domestic origin, so we cannot answer this from the table directly, or we can say probability is 0. So instead of that, we are going to now use our naive Bayes. So I call this thing, I call this data as X now. Okay, so X means these three values of X1, X2, X3 respectively. Now what is asked? It is stolen equal to yes, given input is X. So go with Bayes, normal Bayes. So it will be X. So this is your normal Bayes. Now we are going to change this particular likelihood using naive Bayes. Okay, so if you see here, probability of yes, then probability of no. So probability of yes is equal to say 1, 2, 3, 4, 5. So 5 by 10 is probability of yes. So probability of no is also 5 by 10. So this is my prior. Note that the denominator calculation is not required to take a decision. Okay, so I can ignore that calculation to take the decision, because that is common for probability yes given X and probability no given X. So I need not calculate that. So what we need to calculate now is probability of red, because my X consists of X, that is red, SUV, and domestic. So this is my data. So this red, if car is of red color, is it stolen? So that is the question here. Probability of getting stolen if it is SUV, probability of stolen get if it is domestic, and opposite questions are no. So this is yes bracket and this is no bracket. So we want all these probabilities to solve this problem. So probability of getting stolen yes is 5 by 10 and no is 5 by 10. So probability of red given S. So let us mark S sample first. So these are S. Out of that, how many times red is appearing? So red is here, red is here, and red is here. So 3 times red is appearing. So it is 3 by 5. Now in yes, that is stolen, how many times SUV is appearing? So SUV and yes. So where is that? Yes, here. So SUV is only 1 time out of 5. So it is 1 by 5. Now domestic and yes. So in yes, so this is domestic, and then 2 times. Okay. So only 2 times. So 2 by 5. Now let us go for the no samples. So I mark no samples 1, 2, 3, 4, 5. So there are 5 samples. Out of that, how many times a red color is appearing for no not stolen? So this is 1 time, and this is second time. So 2 by 5. The third one is within not stolen cars, how many times SUV is appearing? So this is no and SUV, no and SUV, no and SUV. So 3 by 5. Then go to this third question, that is probability and car is domestic and getting not stolen. So third is domestic. So this is 1 time, 2 time, and 3 time. So 3 by 5. So I hope everything is now known to us. So we can answer the final question. So what is final question? Final question is this: probability of getting stolen given x. X is that 3 values of these 3 variables, that is color is red, type is SUV, and origin is domestic. Okay, so use now Naïve Bayes. So I can write here. So this will be equal to probability of color equal to red given it is stolen, yes, into probability of, just 1 second. Okay, so this will be the use of Naïve Bayes. Now you have to just substitute the values here. So that I have done here. So 3 by 5, 1 by 5, 2 by 5. So these are these 3 terms. Okay, multiplied by probability of yes and divided by probability of x, that is input. So I am keeping that thing as it is here. So it will be equal to 0.024 by p of x. Now same thing you will use for the question, that is probability of getting stolen is no, given input is same, that is x. Then these 3 are the likelihood approximation, and this is the prior of no, divided by probability of x. So this will be 0.72 0.072 by p of x. So from this we can see that probability of yes given x is greater than, sorry, less than probability of no given x. Am I right? So thing is that your answer is no. So getting stolen with x is equal to red, SUV and domestic. Your answer is not stolen. Okay. If you want exact now probabilities, then we need to calculate probability of x. So what I do, I just add these two probabilities. So I just say this two probabilities equal to 1 and substitute their values. Say this and this. Sum is equal to 1. Then I calculate p of x directly, that is 0.096. Now with this 0.096, I substitute the value here and here. Then I get 0.25 and 0.75. So probability of no is 0.75 and probability of yes is 0.25. So answer is no. Okay. So like this we can easily solve for this kind of tabular data, and even though some samples are missing, still we can calculate the probability and find out the answer. So that is the beauty of naive Bayes. So if you have any doubt, you can ask, otherwise we can leave. How was your paper? Any comment?